A necessary condition for an estimator to be consistent is that the probability limit of the estimator is equal to the true population parameter being estimated. So if we're using this estimator here based on n observations, which are IID taken from a population with expectation mu, this would be a consistent estimator if the probability limit of the estimator, that is, it converges with probability towards the true population parameter mu. Now, in order to analyze this, we can simply useplims. So the plim of mu1 hat, we're basically looking to see what this estimator converges to as the sample size converges to infinity. So we're going to take theplims, the probability limit of our estimator, n plus 1 over n squared, times by the sum from I is equal to 1 to n of xi. Now, before we do this, we need to know a little bit about rules relating toplims. Well, there's one rule that we'll use again and again and again, which is the weak law of large numbers. And the weak law of large numbers states that the probability limit of any sample mean, provided the observations are IID, is going to be equal to the expected value, or in this case, because the expected value is mu, it'll just be equal to mu. So that's a law that we can use again and again and again. The probability limit of a sample mean is equal to the expected value in the population. There are also a few rules that we can use relating toplims. The plim of a sum is just equal to the plim of A plus the plim of B. So the plim of a sum is the same as the sum of the plims. Unlike with expectations, the plim, the probability limit of a product, is going to be equal to the product of the plims. Similarly, the plim of a ratio, provided the plim of B is non-zero, is equal to the ratio of the plims. So we're going to use at least one of these rules in this example. So we've got an estimator that we're trying to examine whether or not it's consistent or not, and the easiest way to address this is to try and write it in some form relating to the weak law of large numbers. So somehow we can write it relating to a sample mean. Now we can rewrite this whole expression, the plim of n plus 1 over n squared times by the sum of the xi's. We can split that n plus 1 over n squared into an n plus 1 over n times by 1 over n times by the sum from I is equal to 1 to n of the xi's. But what we've got here is just a sample mean multiplied by something. So we're going to use the fact that the plim of a product is equal to the product of the plims to write this as the same as the plim of n plus 1 over n times by the plim of 1 over n times by the sum of the xi's. Now, by the weak law of large numbers, this second term is just going to be equal to the expectation of x. So this second term is just going to be equal to mu. The first term, we need to think about what n plus 1 over n converges to as n tends towards infinity, but n plus 1 will tend towards infinity at the same rate as n, so the plim of n plus 1 over n will turn out to just be equal to 1. So our plim is just equal to mu, or the expected value of x. Since this is the same as the thing that we're trying to estimate, we can say that the estimator is consistent. That is, it converges with probability to the true population parameter as the sample size it tends towards infinity. So therefore it's a consistent estimator.